Topic 2, Chemical Reactions, Lesson 1, Mixtures and Solutions, which can be found on pages 68 through 76 of your textbook. All right, we're going to start off with the connected. So the first thing it tells us to do is, what are the components of the sand and the seawater? And then write the answers in the boxes on the photograph. So that's to the right of your workbook, and we will go over that on the next slide. So before we do that, let's go into our question. Suppose you are a researcher studying these components. You need to separate the shell fragments from the sand, and you must also extract the sea salt from the seawater. Describe how you would do this. So an acceptable answer would be, I would use a sieve to separate the shell fragments from the sand. I'd use a pot and stove to boil the seawater in order to separate the water from the salt. Your answer does not have to look exactly like this, but it should contain similar information. All right, so moving on to the components of the seawater and sand. So the seawater is composed of salt, water, and particles of matter from fish and underwater plants. It may also contain contaminants. And then sand is made up of shell fragments, tiny bits of rock, and materials. And your answer should look something like this. It doesn't have to be exact, although in this case, I think writing exactly what I wrote would be a good idea. Types of mixtures. So a mixture is made of two or more substances that are together in the same place, but their atoms are not chemically combined. So we have heterogeneous mixtures, and those are ones that features distinct components that can easily be seen and sorted. And we have homogeneous mixtures, which often look the same throughout the entire mixture. So a homogeneous mixture, you could think of something like grape Kool-Aid. It looks the same throughout. It's all purple, the sugars dissolve, the Kool-Aid mix is dissolved. A heterogeneous mixture would be something like a lava lamp. You can see what the oil-like substance versus the water-like substance within it, but they're mixed in the same place. Separating mixtures. Remember that the individual components of a mixture keep their properties. This means that the properties of the components in a mixture can be used to separate them. So mixtures that contain particles of different sizes, for example, can be filtered so the larger particles are removed from the mixture, i.e. the rocks from the sand. Rocks are larger than the sand is, so we're going to filter them out. Mixtures that have magnetic components can be separated with a magnet. So another, if we're on the beach and we're looking for coins in the sand or jewelry, whatever, we're going to use a metal detector to find them. That kind of concept. You could use a magnet to find something that's magnetic. So if you're like in a wood shop and you dropped nails or screws in wood shavings, you could use a magnet and hover it over to try and pull up all of the nails or screws. Liquid mixtures can be heated until some components evaporate and others are left behind as solids. So that would be like salt in seawater. So if you boil the water, eventually all of the water is going to evaporate, and what you're going to be left with is the salt. All right, so the planet. The right tool for the job. Figure 2, 3 different mixtures need to be separated in order to analyze each component. You have 3 different tools available to get the job done: a magnet, a filter, and a hot plate. Identify which tool can be used to separate each mixture. And then the reading check is to explain. So for each mixture, identify its components and explain how their properties can be used to separate the mixture. So in our first, we have sand and iron fillings. So we're going to use a magnet. And like I said earlier, the components and how they are separated: sand and iron fillings are magnetic, while sand is not. So the iron fillings will be attracted to the magnet, leaving the sand behind. Very similar to what I was talking about in a wood shop with screws and wood shavings. Similar concept there. Now the salt water, the tool we're going to use is going to be the hot plate. So the components are salt and water, and the hot plate can be used to evaporate the water, which is going to leave the salt behind. I've also talked about that previously on the prior slide, so you should have gotten that pretty quickly. Muddy water. So obviously we're going to use the filter for muddy water. The components are mud and water, and the larger mud particles will remain in the filter while the water passes through. Classifying mixtures. Honey, oil, and vinegar, salad dressing, and milk are examples of different types of mixtures that may be found on your dinner table. The three types are defined by the sizes of their particles and how the particles behave. So here we have a good example. We have the still nut, which is stuck in the honey. We have corn syrup. The honey is the most viscous, corn syrup a little bit less so, and then maple syrup. Then we have milk, dish soap, water, canola oil, and rubbing alcohol. So all of those things are different and have different requirements, and that is why they stay in those nice little layers. Moving on, so colloids. So a colloid is a heterogeneous mixture containing small undissolved particles that do not separate or settle out if the mixture is undisturbed. So the particles of a colloid are too small to be seen without a microscope, yet they are large enough to scatter a beam of light. This is why they are not clear. Paint, whipped cream, fog, and smoke are all colloids. So in this image to the left, you can see the flashlight, how the light goes very much through the solution that is clear. It kind of goes through the colloid, and it doesn't really go through at all the suspension. All right, so next to the colloid topic, we had figure 3, fog. And it said air is a homogeneous mixture that light rays can pass through. Fog is an example of a colloid. The densely packed water molecules prevent most of the light rays from passing through. In the circle, draw the particles in the fog to show how the light is scattered. So it's going to look something like this above with the fog and the light, but you need to make sure that you have particles exactly at that intersection point where the arrows divert. All right, suspension. So a suspension is a mixture with particles that can be seen and easily separated by settling or filtration. For example, a bottle of oil and vinegar salad dressing will settle out into its constituent parts if left undisturbed. Muddy river water, as shown in the picture to the right, is another example of a suspension. So figure 4 says swiftly flowing river water may have a heavy load of suspended sediment. If collected in a jar and left undisturbed, the sediment will settle out or settle into the different parts, like it does in this jar here. Solutions. A solution is a homogeneous mixture of a solvent and one or more solutes. The solvent is the part of the solution that is usually present in the largest amount. So usually it's some type of liquid, but not always. Water is a universal solvent. A lot of things dissolve in it, but there are other things that can be solvents, of course, also. So it dissolves the other substance in the solution. So that's how you know it's the solvent. It's the one that dissolves the other substance in the solution. The solute is the substance that is dissolved by the solvent. So in grape juice, water is the solvent, sugar and the other ingredients are all solutes. Molecular solutes. Molecular compounds such as table sugar break up into individual molecules in water. The sugar molecules are polar like water. The water molecules attract the sugar molecules, and the sugar molecules move away from one another. While the water molecules surround the sugar molecules, the chemical bonds do not break. Most nonpolar molecules are not soluble in water. Ionic solutes. So here we have figure 5 forming salt water. So observe what happens in each step as salt dissolves in water. So we have table salt, sodium chloride is placed in water, H2O. Then the negative oxygen side of the water attracts the sodium ions, which are slightly positive, and the positive hydrogen side of water attracts the chloride ions, which are slightly negative. Water molecules surround individual sodium and chloride ions, and the salt dissolves. So sodium chloride is made of positively charged sodium ions and negatively charged chloride ions. These charges allow salt to dissolve in water. Water is a polar molecule due to the arrangement of oxygen and hydrogen atoms. The oxygen side is slightly negative, while the hydrogen side is slightly positive. The attractions shown in the picture are what makes salt soluble in water. So our reading check. Many people refer to water as the universal solvent. Why? And that's because many different substances can dissolve in water. Concentration. So solutes raise the boiling point of a solution above that of the solvent. For example, under standard atmospheric pressure, pure water boils at 100 degrees Celsius, whereas salt water boils at 102 degrees Celsius. Solutes also lower the freezing points of solutions. While the surface of a lake may freeze at 0 degrees Celsius, the salty ocean freezes at 1.8 degrees Celsius. Boiling point, freezing point, and density are physical properties of solutions that are affected by concentration. A concentrated solution has a lot of solute. A solution with little solute is a dilute solution. For example, a cup of tea will become more concentrated or stronger if it's left to sit, so some of the water evaporates. The tea will also be more concentrated if the tea bag is allowed to steep longer. And here we have a visualization of high concentration of water versus low concentration of water. And you can see the different dots, so the small blue dots, there's a lot less in the low concentration because there's a lot less solute in the low concentration of water than in the high concentrate. All right, so for our math toolbox here, salinity or the concentration of salt in seawater varies in different parts of the ocean. The salinities of 2 seas are labeled on the map in PPT or parts per thousand. This means that the Baltic Sea has 10 units of dissolved salt in every 1,000 units of seawater. So question 1, suppose you collected 100-gram samples of seawater from each of the 2 seas. Determine how many grams of dissolved salt you would expect to find in each of your seawater samples. Write the values in the appropriate boxes on the map. So for Baltic Sea, it's 10 ppt, so that's 10 over 1,000. You're going to make that equal to x over 100 because we have 100 grams of water, but we don't know how much salt is in that, and that's what we're looking for. So then we're going to solve that by multiplying by 100 on both sides, and we're going to end up with 1 gram. Then for the Red Sea, it's 40 ppt, so that's 40 over 1,000. The same thing, x over 100, because we don't know how many grams of salt there are. And then we're going to multiply 100 by both sides to get 4 grams of salt. Now, from which sea would you take water sample that would be easier to freeze? Explain. So the Baltic Sea would be easier to freeze. It is more dilute solution, so its freezing point is slightly higher than the more concentrated Red Sea. That's because it has 1 gram as opposed to the 3 more grams in the Red Sea at 4 grams. Solubility. So solubility is the measure of how much solute will dissolve in a solvent. A solution that can no longer dissolve a solute is saturated. The properties of the solute and solvent affect solubility, and temperature and pressure also play a role. Temperature. In general, raising the temperature of the solvent increases the solubility of a solid solute. This is one of the reasons we make soup broth on a hot stovetop, because the solid solutes, such as table salt, dissolve more easily if the solvent has a higher temperature. The higher temperature means the molecules of the solvent are moving faster. These more energetic particles can more easily break up the solid solute. Solubility and temperature. So as temperature increases, solids become more soluble, but gases become less soluble. Because carbon dioxide is less soluble in warm water, a cold carbonated beverage is more bubbly than a warm one. So here we have solubilities of substances in water. So we have the substance names, so sodium chloride, silver nitrate, sucrose, etc. We have measurements taken of how many grams per 100 grams of water at 0 degrees Celsius, 50 degrees Celsius, and 100 degrees Celsius. So based on what you have read and the data in the table, do you think silver nitrate is a solid or a gas? And we're going to say it's a solid. So its solubility increases with increasing temperature, which is the general rule for a solid solute. Gaseous solutes are less soluble with increasing temperature. So we know hydrogen, oxygen, and carbon dioxide are all gases and they have very small numbers, whereas our silver nitrate had 122, 455, and 733 as composed to our near zero numbers of the gases. Pressure. The solubility of a gaseous solute increases as pressure on the solution increases. As with a can of soda, a sudden release of that pressure can cause bubbles of gas to come out of solution. If the diver swims upward too quickly, nitrogen would suddenly come out of the blood and get lodged in blood vessels. The best way to avoid this painful condition is for the diver to swim up very slowly. That way, any dissolved nitrogen has time to leave the blood through the lungs. So this is an example of using this principle in a real-life situation. So that's why when we have divers, we want them to move up more slowly because of this principle, like I just said. All right, what happened? Figure 7. Picture yourself on a dive boat. Someone has just climbed aboard the boat after an hour-long dive, complains of pain in her joints. She loses consciousness. You check her dive computer, which appears to be flashing a warning sign about decompression stops. You click a button to reveal a dive profile, a graph that plots how long the diver spent at different depths over the course of her dive. The graph is shown here. Circle the area of the graph that represents the diver's rise to the surface. Based on the graph and figure caption, what do you think happened? So we're going to circle this area over here to the right where she comes up, and she went beyond 18 meters, so the nitrogen in the air she was breathing was soluble beyond that point. She then ascended too quickly, which caused the nitrogen in her blood to come out of solution and form bubbles. The bubbles are blocking her blood vessels and causing her harm. All right, so that covers lesson 1, and now it's time to do the lesson 1 check. So based on its physical properties, is a colloid a homogeneous mixture or heterogeneous mixture? And how does it differ from a solution? A colloid is a heterogeneous mixture because the particles in it are not dissolved. A solution is a homogeneous mixture. The properties of a solution are the same throughout the entire solution. 2. The table shows the solubilities of 3 different substances in water at the same temperature and pressure. Which of the substances would have the greatest mass dissolved in 100 grams of water at the point of saturation? Explain your answer. We're going to say silver fluoride has the highest solubility, so more of it can dissolve in water than the other substances. It would have the greatest mass in water at the point of saturation, which is when no more solute can dissolve. So basically, because silver fluoride had the greatest solubility, so 172 grams per 100 grams of water, which was far greater than the 45.8 and 65.3 that aluminum chloride and potassium bromide could do respectively. So that's why it's going to be best. Moving on to 3. A carpenter has a mix of both iron nails and plastic nails in a jar. For a job, he needs only the iron nails. What physical properties could help him separate the nails? That's going to be magnetism. So the iron nails are magnetic, so he could separate them with a magnet. They are also more shiny than plastic, so he could separate them by color and or shininess. The fastest way, of course, is going to be by magnets. So lastly, you and a friend want to start a soda company. For ingredients, you have sucrose, which is table sugar, carbon dioxide gas, concentrated juices from different fruits, and water. Describe how you will experiment with these ingredients to develop a recipe for your soda. Consider the roles of temperature and pressure and how to minimize the cost of energy in the production of your soda. So your answer should describe a plan to find out how much sugar and concentrated fruit juice can dissolve in a standard soda can volume of water at different temperatures. So that's what you're going to be doing, and you're going to explain how you can do that in some way, shape, or form. And once you've done that, you've completed your lesson 1 check.